LeChatelier's principle. Let's go ahead and get going. Banana.
Got it.
So, I am recording, folks. I love how conversations are still going on, doing their own thing, just chilling, acting like I'm not up here talking. This is going to be a really interesting recording for those out there in the real world wanting to learn a little bit about LeChatelier's. Okay, so LeChatelier's principle. You guys have had an exposure to this in all levels of chemistry. So this is going to be somewhat of a review, and then we're going to do the math application of it. But basically what it says is that when a system is at equilibrium, happy-go-lucky, chilling out at equilibrium, and you stress it out, it's going to shift in response to alleviate that stress. So we have Werner here. He looks like he's at equilibrium. He's chilling. So I'm going to stress him out, and those of you who had me before have seen this before. I'm going to stress him out. What is he going to do to get back to equilibrium? He's going to push back the opposite way, right? He actually pushed back. I usually have one of two problems with that demo. Usually, sometimes I'll push people back like today Catherine did, and I push her back and she just stayed like that, and she didn't push back. And then, or then I'll have the person that like pushes so hard against me I can't push him back. So you did well. Congratulations. All right, so he's a normal equilibrium system. So how do we stress out a system in the chemical world? We can change concentration. What's going on? Why is it so talky? We can change concentration of a reactant or a product. We can change the volume of a system, which only affects the gases, but it does cause a stress. Or we can actually change the temperature of the system and cause shifting. Change temp. So we're going to look at all of these three things individually. First is concentration. So let's pretend we have this system, AB, making AB. And if I were to mess with the concentration and say, for instance, I dump in more A2. In response, the system then wants to get rid of the A2 in order to get back to that same product-to-reactant ratio. So which way does it have to shift hard in order to do that? Shift to the right. So you can say right shift, or you can say forward reaction is more favored. Okay? What happens if we add AB to the system? Remember, this stuff is all free-floating in a beaker. There is no left and right side, theoretically. We're just talking about the production of more one way or the other. So if we add more A and B as a product, what's going to happen? It's going to shift left to get rid of the AB that we made. And it'll shift more favored in that direction until it gets back to that same K product-to-reactant ratio. You can also take away reactants and products. So if we, for instance, remove B, take B out, what is it going to do? It wants to replace the B, right? So it's going to shift to the left. So how do you take stuff out? Like, how does that work? Well, if you have a reaction, I'm kind of just making something up right now that isn't necessarily an equilibrium reaction. Let's say we have that. So pretend we have this. If I were to, add Ag+, we assume it would shift it right? All the normal stuff. But sometimes we add things, and you might say, oh, that doesn't affect the equilibrium because it's not in the system. If I were to add Cl-, for instance, to that, on the onset, you may be like, so? It doesn't affect. What does adding Cl- potentially do? It makes AgCl, which is an insoluble solid. So that is the same as saying we're removing Ag+. Make sense? So you need to watch out for that. Before you ever say, oh, no effect, it's not in there, stop and ask yourself, do I form any liquids, do I form any gases, or do I form precipitates when I do that? Another example is if we add acid to this system. What is that H+ going to do? Not neutralize it. What is it going to do? It forms water, which is the same thing as removing OH-, again, making that shift left. Okay? So just know when you are adding something that isn't in it already, it could potentially have no effect, yes, or it could end up messing around with one of the reactants or products and removing it. So just pay attention to that. All right, so concentration is pretty straightforward. Let's talk about volume. Now, the important part about this one is it's kind of a multi-step process. I need you to convert volume to pressure and then ask yourself, okay, what is it going to do in response? So let's look at this, and we're going to do this both ways. I'm going to say, okay, we are going to increase the volume of this system. When we increase the volume, I want you to convert that to what we did to pressure. When we increase the volume, what does that mean we did to pressure? Decrease the pressure. We decrease the pressure, so what does the system want to do in response? Increase the pressure. So how does a system of gases increase pressure? More moles. So if this needs to increase its pressure, it's going to shift to the side with more moles of gas. Gas, gas, gas. Only look at the gases. So which way would that be in this case? We're going to shift to the right. Because this is 1 mole of gas, this is 2. So this is kind of like my low pressure side. This is kind of like my high pressure side. So let's just look at the reverse really quick. If I decrease the volume, pressure is, what did I do to the pressure? I increase the pressure. In response, it wants to decrease the pressure, so it's going to shift to the side with less moles of gas, which in this case would be to the left. Questions? Do we get it? Okay, I hope so. Y'all are awfully quiet when we're in content, but pretty talky when we're not lecturing. All right, this one, temperature. Temperature is super simple once you identify whether the reaction's exo or endothermic. And I want you to write the word heat on the appropriate side. So in this problem, it says the reaction is endothermic. It'll either tell you it's endothermic or it'll give you the value of the delta H. And you can tell from the positive or negative this is endo or exo. So if it's endothermic, I want you to write the word heat on the appropriate side. In this case, it's a reactant. It's entering. If it were exothermic, you would have written heat on the other side. Then you treat it just like concentration. If I heat up this reaction, it means I am adding heat. If I'm adding heat, it needs to get rid of the heat and cool itself down, so it's going to shift. Which way? Right. Okay. If I'm cooling this down and taking away heat, it wants to heat itself back up, and it's going to shift left. Okay. And then exothermic will be absolutely the opposite of both because it's going to be on the other side of the equation. So just write the word heat where it needs to go. So let's just jump in and do a problem with it. Okay, here we have a reaction. Delta H is negative 1036. Given the reaction is at equilibrium, predict the direction the reaction would shift when disrupted by each of the following. The amount of H2O is increased. Okay, that would be correct, but there's something that we missed. No? Oh, well, we'll do heat in a minute. We can do heat. Sure, we can do heat, but that's left is incorrect. Why is left incorrect? It's a liquid. Anytime you have a liquid or a solid, there is no effect on equilibrium. We do not put it in the equilibrium expression, so there will be no shift. Liquids and solids, okay? Now, Amelia mentioned the heat thing. Yeah, we can address that. What is this heat telling us, the delta H? It's exothermic because it's negative, so where are we going to write the word heat? On the product side. So if we get a question about it now, we'll be able to address it. All right, and number 2, we do need that. The temperature of the reaction is increased because this is exothermic. We're increasing the heat, and it's the product that's increasing here. So which way is it going to shift? That's going to shift to the left. All right. The volume of the container is decreased. Now we have to talk through this. I don't want you jumping. I have a lot of students say, oh, decreased volume means increased pressure, so we have to shift right. No, or shift to the high pressure side. When we decrease the volume, we increase the pressure. So it's got to do the opposite of that. So decreased volume means increased pressure. So what does it want to do to the pressure to get back to normal? Decrease the pressure. So we're going to shift to the side with more or less moles of gas? Less. So what side has less moles of gas? The right. This has 2 moles of gas. That has 5 moles of gas. So this is our low pressure side. So shift right. By producing less moles, it's decreasing the pressure of gas, moles of gas. And the last one down there says the amount of H2S is decreased. We take away H2S, take away H2S. It wants to replace it by shifting left. Okay, so those are pretty simple LeChatelier's problems. It doesn't get much harder than that because they just pretty much ask you the same kind of stuff over and over again on those. Where LeChatelier comes into play, though, is when we have to do rice tables. We need to calculate something called Q. I call Q the fake K. Fake K, or the K wannabe. Q wants to be like K. So ultimately, what we do in a case like this, and when you would see it in a scenario, is when you do a rice table and you put in all the initial concentrations and there are no zeros. What did we do with the zeros yesterday? What did the zeros help us figure out? Which way we shift, right? So if we had a 0 in the initial line of the rice table, we shifted toward that thing. Well, if you have all numbers, we got to figure out which direction to shift. And that's why we use Q. We figure out the exact same ratio. It's still products over reactants, but this is the same ratio before equilibrium. By knowing the ratio, we can compare it to Q. We compare this Q to K and go like, oh, this needs to get bigger to be like K, or this needs to get smaller to be like K, so we can figure out the shift. All right, so let's actually do that in this next problem. I don't want you to read this yet because this is ultimately what you need to know. I don't think you need to memorize it. I think you can rationalize your way through it just knowing that Q wants to be K. Knowing that is all you need to know. The rest you can think through logically. So here are some examples. Pretend these are rice tables, right? So this would be the initial concentration. We have the reaction. So this is the reactant, and these are the 2 products. Looking at that, simple enough, what direction would we have to shift in order to get to equilibrium? The first one. To the right. Why? Well, because we have zeros here. We got no product. So we're going to have to lose and gain and gain. So this, the answer, which direction would this reaction proceed? The answer is to the right. That's easy. Okay, let's look at this one. Here we have our reactant and our product and our product. Which way would we have to shift this time? We're going to shift to the 0. Y'all are way too quiet. I can't handle it. We're going to shift left. How are we going to shift, everybody? Okay, I'm going to keep doing this until you actually respond to me, so you might as well just give in so we can get done. We're going to shift left, so we're going to lose, and gain here because it's shifting toward the 0. Okay? Where we see some interesting stuff when we do the rice table is in a case like this. Notice we have concentrations in all our initial spots. So I'm just going to kind of start the rice table. We have NOBr, and then it's going to NO plus 1/2 Br2. That was the reaction. So my initial concentration I have is 0.1, 0.1, and 0.1. This is the scenario where we have to calculate the Q. Did they give us the K in this problem? What was that K? Okay, so that's our K. This is our goal. So what we're going to do is we're going to calculate Q. We're going to do the same ratio that you do for a K calculation. Products raised to the coefficients divided by the reactants. So we have 0.1 to the first times 0.1 to the half products over 0.1. So what is our numerical value of Q? Calculators, folks. I need calculators. I need y'all working. Come on. I'm working way too hard to get y'all engaged today. 0.316, 0.316. Okay, so looking at Q and looking at K, what's the relationship? Q is greater than K. Q wants to become K. Remembering that this is products over reactants, Q wants to get smaller in this case. To get smaller, do we need more products or more reactants? More reactants. That'll make us numerically smaller. To make more reactants, which way do we shift? Left. So you don't have to memorize all that stuff. Just know Q wants to be like K and make it shift to do that. Now there is kind of a number line trick I'm not real keen on sharing, but if that made absolutely no sense to you, you can draw a number line and you can look at the relationship. If Q is bigger than K, we know that Q would be to the right of K on a number line, right? So remembering Q wants to become K, whoop, which way does it go? Left. It shifts left. So that's a trick. But again, not fond of the trick. All right, so you guys calculate. I'm not going to, I'll kind of be rewriting it. Y'all be calculating it. Again, we have all the initial concentrations, so you have to determine this concentration. So it's we're going to find Q. What is our Q here? It's 0.079. Did I write my expression correctly? If Q is 0.079, what does that mean? It doesn't shift. Why? It's already at equilibrium. It has already met the reactant product ratio requirement to be at equilibrium. So this would be no shift. I'm going to make sure this stays with this. Got to be really careful as a teacher. I can't use how many times I've accidentally left my F out. It happens. It happens. Anyway, so questions? Are you okay? Got it? You had a light bulb all of a sudden. So. Oh, my joke? Yeah. Okay. It's all right. You're allowed. It's okay. That's good. That just means you're an innocent mind, and there's nothing wrong with that. The world needs more of that. Did I? I'm sure I did. Yeah. I always make silly things like that happen. Okay. So this is an example of a kind of problem you would have to do. Let me preface this with this and the next problem, 12 and 13. The math of solving for X is redonkulous. We're not going to make you do that. However, we've got enough smart people in here that have the 89s and that know how to graph and do all that stuff that we can figure out the answer. But you will not be responsible for this level of algebra on the test, okay? The setup and then the shifting and all that kind of stuff, yes, you can do. So let's go ahead and look at this. It's this Kc is 19.9 for this reaction. Find the equilibrium concentrations of all species. So we're looking for everything on the E line. And then they give us the initial concentration pretty much of everything. So we're going to start our rice table. Cl2, these are all gases. That's awesome. And then I is, initial concentration is 0.4, and this one is 0.2. And this one is 7.3. Which way are we going to shift, y'all? You can't just say left or right without calculate. It's like I didn't even talk about Q. No, we can't just say left or right. It's not a 50-50 shot and you hope to go the right direction. You need to calculate the actual Q. And yeah, it is left just because of the super high concentration at CLF, but it's not going to be that obvious at all times. And you need to calculate Q. That's all I'm saying. So we're going to use the initial concentrations and do our 7.3 product squared over our 0.4 reactant times our 0.2 reactant. And we're going to get a Q of, looky there. See, it keeps showing up. I'm telling you, it's evil stuff. Q does not want to stay that way. Nobody should want to stay that way. We need to shift and make Q equal to K. So at this point, Q is much bigger than K, right? So for Q to become like K, it needs to get smaller. Do we want more product or more reactant to get smaller? More reactant, so that is a left shift. We haven't done this yet in class. We're going to lose here this time and gain and gain. So we lose 2x, gain x, and gain x. This doesn't change that we're doing products over reactants. It doesn't flip anything. We just do it like we did yesterday beyond this point. So our equilibrium here, and you're going to see pretty quickly why this is disgusting math. All right, so to solve for this now, we're going to solve for x, and we're going to write our equilibrium expression of CLF squared, unfortunately, times CL2 times F2. So when we plug our stuff in, our K, what is K? 19.9. And that's equal to 7.3 minus 2x squared. I promise you I will never make you foil in this class. You will not be foiled. So yeah, is this solvable? Sure. But this is not a math class. This is not higher level advanced graduate student chemistry where we really need to be crunching numbers to this degree to find a flippant equilibrium concentration. I'm not going to have you do this. Anything beyond the simple quadratic is not going to happen. So, does anyone have an 89 in here? I have an answer. What did you get? Yep, 0.92. They had 0.93, but that's cool. 0.926. It looks it should be actually 160. We're going to say 0.93. So x then comes out to be 0.93. Do you remember the negative root, what it was? Okay. So this is the winner. All right. So now we can continue. We let technology do all that work, and we're going to go ahead and write our final equilibrium concentrations. Cl2 now, we're going to take our x and plug it in, is, math is hard, 1.33? 1.33 moles per liter. F2, 1.13 moles per liter. Yeah, and I can't do this one in my head. What's CLF equilibrium concentration? 5.44 moles per liter. This is when math is hard, has real meaning. Questions about the shifting, questions about the process, not the solving of x, the process. All right. Next problem. Go ahead on your papers. I'm going to be quietly working. I want you to figure out direction of shift on your own by calculating Q, okay? And I'm going to quietly write this for the people at home. Okay, so I'm going to put it in my calculator and see what I get. Oh, clear. Do y'all ever like type a whole thing in your calculator and then look at the screen and realize it's not even on? Yeah, that's what I just did. All right. Did we get this? Okay, that's Q. Our K is equal to 170. So Q is less than K. What do we do for shifting? If Q is less than K, it needs to get bigger. We need more product to make Q like K. Got to shift to the right. So we're going to lose 2x and gain x. And it's 0.015 minus 2x and 0.025 plus x. So I'm sure some of you are ahead at this point. If you are, get that answer ready for when I'm done. N204 over NO2 squared. And so we have 170 equal to, oh Lord, this is another one that's just beautiful. Whoa, 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 wrong, go away. No, this is not squared. Ah. Yeah, it does. I have trouble with their solver. I'm going to talk about a way to solve for this if you don't like the solver. I just want to get this stupid thing set up, and I keep messing it up. Urgh. Divided by, this is the squared one. This is why you do the unsubstituted equation. You catch yourself from not squaring or squaring the inappropriate things. Okay, so what you can do, if you're curious on how to solve something like this, you can do a solver, because the TI-84 under the math button has a solver, which I never can get to work right. I don't consistently understand it. What you can also do is you can take your denominator and just cross-multiply, basically. And this is a pretty interesting way to do it. It's to do it graphically. So you go into your y equals situation, and you put this one side of this equation into one of the y's, and then you put the other side of the equation into the other y. Graph them, and what do you look for? Anyone know? The intercept. Yeah, where it intercepts, and that will give you the value. And it worked, because I had someone do that as well as a TI going at the same time, and the TI-89, and got the same answer. So that's kind of a sexy way to do it. But you're not going to be in that position. I'm not, like I said, I'm not going to make you be solving this under normal circumstances. So what did y'all get for x? Anybody get it yet? What'd you get? Like 0.199. Yeah, and that can't work. Close. There's a second root. 0.015 was originally what they got last period, but if you look at the original concentration, minus 2x, that can't be it. That's it, 0.0013. Is that what you got, Naira? 0.0013 is actually the answer. Well, no. I'm having a brain dead moment. So my NO2 then is equal to 0.015 minus 0.0026, and what is that? Okay. And then 0.025 plus 0.00, it's 0.0263. And that is of the N2O4. Okay? Again, I'm just concerned you know the process, not how to solve for that stupid x in that particular equation. So we good with knowing how to shift, direction of shift? All right. We have one last problem to do. has nothing to do with Q. I'm just throwing this in because, you know, I'm sure you're curious. You might not be curious, but everything we've done up to this point has had all gases or all aqueous in the reaction, and we haven't had to really worry about it. Well, in this case, if you notice, we have a reactant that's a solid. And we need to figure out how to solve for the equilibrium concentrations of these two guys here, given the reactions K. It's still a Rice table, and we're still going to set it up exactly like you know. And it seems scary, but I am telling you, it makes your life so much easier when you do have something like this. So this thing right here is a solid. Whenever you have a solid or a liquid, bink, does not affect our equilibrium. So what's going on? This happens to be a salt, and it doesn't matter how much you really start out with. If you throw in 5 grams of salt into this container, the reaction's going to happen. If you throw in a kilogram of salt into the container, the reaction's going to happen. And it doesn't matter how much you start with, because at the end of the day, the amount that's going to go is based on the K value, which only depends on these two things. So we don't care our initial concentration, all right? Do we have an initial concentration of the other two? No. Right now we're just throwing the salt in the flask, and it's going to just start to decompose to make that stuff. So we have 0 here. Now, do we lose here? Yeah, we lose, but again, there's so much of it, it doesn't matter. You're not going to even be able to know, it's not concentrated. You're not going to be able to know how many moles, whatever. No effect whatsoever, but we do gain and gain here based on the 1-to-1 ratio. So all we have here is X and X. Our equilibrium expression is super easy. What is it? NH3 to the first times H2S to the first. Do I put it over anything? No, that's it. That's the expression. So to solve for the concentration then of these two guys, all we have to do is do 1.8 times 10 to the negative 4th is equal to X squared, X times X. So cutting out that guy right there makes life a lot easier. So X is equal to, which is equal to the concentration already of these two. What is my numerical value? This 0.013, correct? Moles per liter. Okay? All right. Look over that next problem. How is that different? Yeah, there's already an initial concentration in there. So everything is the same except you have an initial NH3 concentration of 0.02. So I'm going to be lazy because that's what I am. Oh, I want this to be this, and I want this to change color. I'm going to replace this here, pink, with the initial concentration of 0.02. Right? So what does that change on my E line? This is 0.02 plus X. So my new expression will be K is equal to X times 0.02 plus X. And I should just put the value of K in there. Bink. 1.8 times 10 to the negative 4th. So this is going to lead us to a quadratic formula situation. This is, I do expect you to be able to do this. That's why we're offering you guys the use of quad form. So this is 0.02x plus x squared is equal to 1.8 times 10 to the negative 4th. I'm going to set the right side equal to 0 this time. So I get x squared plus 0.02x minus 1.8 times 10 to the negative 4th is equal to 0. So now you have your A, your B, and your C. You put it in your quad form. Someone tell me what the 2 roots of x are. All right, so we're going to go with the 0.0067 then. So our concentration of H2S is equal to the X, which is 0.0067 moles per liter. And then our concentration of the NH3 is equal to is it 0.0267 moles per liter. And those are my 2 concentrations. This is not beyond the scope of what you might see. I can totally see you getting something like this. All right, so tonight, your homework is B and the pre-lab. So you can work on either one. You've got about 10 minutes in class, and that is it. Tomorrow's lab day. Yay.